Hi, this is a video to help you out with one of the parts of the differential equation questions that's given students some troubles. I'm getting a lot of questions on this. So this is number 7 in your packet, and I'm actually not going to go over part B. That's the typical solve the differential equation and find the particular solution given the initial condition. Definitely good to practice, but the one that I want to go over right now in this video is I want to go over part A, because there's a lot to this question and it's going to help us review some skills from first semester and hopefully make some good connections here. So just to take a read through it, one thing that I have noticed is this confuses students. It's telling us that there's a particular solution, but it's not asking you to find it. Down here it says, hey, find y equals g of x, and now they've defined it as g of x instead of f of x, which is weird. But don't worry about that whole sentence. I just skip over that. And I'm going to pick up here. So we've got this part in the second line that says such that the line y equals -2 is tangent to the graph of f. So then they're asking us to find the x-coordinate of the point of tangency. And then there's a second part. I'm going to stop there and come back to that after I figure out the x-coordinate of the point of tangency. So a couple things I'm picking up on here. Y equals -2. What kind of a line is that? We know that's a line. Yeah, that's a horizontal line. So I'm just kind of vaguely starting to picture this in my head, like maybe my curve looks like that. And it's got to be, there would be my tangent line. So I know I said I was going to come back to it, and I am going to come back to it, but they're asking like local minimum, local maximum, and I'm thinking, oh, okay, it looks like we might have a minimum or a maximum. I just drew one potential curve, but we could have this potential curve as well, where we have a horizontal tangent. And then we also could have this case where we have a horizontal tangent and it's flattening out, but not actually at a maximum or minimum. So back to the question, find the x-coordinate of the point of tangency. This is a working backwards question. Usually what we've been seeing a lot of is write the equation of the tangent line at a particular point. So this one, they're giving us the equation of the tangent line. So we've got this y equals -2. Another way to think of that is y equals 0x minus 2. Why would I write it that way? Well, I'm trying to figure out what to do, and this is kind of triggering me to think, oh, wait a second. My slope is 0. Horizontal line slope is 0. What do we call slope in calculus? Derivative. So the derivative is 0. Remember when I said working backwards? That has to be equal to 0. So where I normally take my dy dx and plug in maybe an x and a y, this time I know that dy dx is 0. The x is what I'm looking for, and the y value is -2. So this point is something common -2. This point is something common -2. Because the y value is always -2. So now I've set myself up to a point that I can solve for x, which is what the first question is asking. Find the x-coordinate of the point of tangency. So multiplying by -2 on both sides gives me obviously 0 equals 3 minus x, so x equals 3 is the x value, of my point of tangency. So that's the first part. Now the second part is to find if it has a local minimum, local maximum, or neither. So there's a couple things you should be thinking when you think relative extrema, basically. I'm going back like 2 chapters, maybe 3 chapters, to when we kind of talked about what does the derivative and the second derivative tell us about a function. So this was kind of our go-to number line. And we now know the point of tangency is x equals 3. So this is probably your first thought. And this is a great thought. We know at that point our derivative is 0. That was implied in the question. But the problem is now when I try to pick points on either side, I pick an x value less than 3 and an x value greater than 3. When I go to plug into my derivative, I have this problem because I can't actually find the derivative unless I know the y value. So that works great as long as my function is defined in terms of x and only x, an explicitly defined function. And that's what we dealt with mostly. So we do have a backup plan. We have another option if that doesn't work out. So I'm going to scratch that because I don't know. I would have to pick a whole bunch of y values and it's just way too complicated. So I did give you like a backup plan. I said, hey, keep this as your last resort because I usually like to use the others, but in the case, especially where we have an implicitly defined function, we have a second derivative test for a relative extrema. So it starts with find the second derivative. So let's go ahead and work that out. So I'm working from my first derivative and finding the second derivative, derivative of the derivative. We're going to have to do quotient rule here, and we're going to have to think implicit differentiation. Great review for upcoming AP test. So I'm going to talk my way through it. I've got denominator times derivative of the numerator. So derivative of the numerator is 0 minus 1, so a negative 1. That's derivative of 3 minus x. Denominator times derivative of the numerator minus numerator times derivative of the denominator. Well, derivative of y is 1, but then I've got to multiply times dy dx because I'm differentiating with respect to x. So the negative 1 would be times dx dx, and therefore I didn't need to multiply by anything. The 1 for my y is times dy dx. That's the implicit part. Don't forget the rest of your quotient rule. Denominator times derivative of the numerator minus numerator times derivative of the denominator all over denominator squared. So denominator squared is just y squared in this case. And good news, I'm not going to actually simplify too much. When we practiced these earlier this year, we made a habit of doing this. We would probably simplify this quite a bit, but then we said we would put our dy dx, which is 3 minus x over y. We would plug that in, and then of course we have a complex fraction to deal with. However, in this case, I don't know that that's even necessary, so I'm going to leave that there, but show you that what we're trying to do is evaluate this at a single point. Because here's the deal. Going back to the concept here of second derivative test for relative extrema, if we already know that the first derivative is 0, which we do, because that was told to us and implied by the fact that we have a horizontal tangent line, we know there's a slope of 0. We know it's either a maximum or a minimum or an undefined because it's changing concavity. So a maximum is always going to be concave down. A minimum is going to be concave up. And then this third case, and I suppose we kind of have a fourth case here that would look like this, but I grouped those two together as that would be my second derivative equals 0. So in the first two cases, second derivative would be negative here, concave down, positive here, concave up, and then 0 here, and that would be no conclusion. So we really just need to figure out the sign of the second derivative. So I'm going to go straight to, let's plug in that point. We now know that the point is 3 comma negative 2. 3 was my x value, negative 2 was my y value that I knew originally. And let's go ahead and just plug that in. So I've got negative 2 for my y, minus 3 minus x value is 3. And then I've got 3 minus x over y, which I could evaluate, but I actually already know that that's going to be 0 because that's my first derivative. That's my slope, and we know that's 0 because, again, we have that horizontal tangent. So remember when I said that we could skip this step? This we could go straight to saying it's 0 because I'm evaluating it at a point. So it kind of depends on if you're just asked to find the second derivative or if you want the sign, or if you want the second derivative sign at a particular point. And then plugging in my y value, which is negative 2, and then squaring that. So I'm just going to keep working this. I've got 2 minus that whole term is 0 over 4 gives me 1/2, which is greater than 0. So I'm ready to make a conclusion. And my conclusion is going to be, since second derivative is greater than 0 at x equals 3, or you could say at the point 3, negative 2, f has a local or relative, let's say local, greater than 0 is concave up, so this is me picturing it has a local minimum. at that point. And I got at least 3 points for this because that would have been 2 points. One for the answer, saying it's a local minimum, and a second for your reasoning. So finding the second derivative sign, and then a point for our initial finding x equals 3. So the reason I love that question, we did work with second derivative tests, but not a ton. So always good to review that. Great to be practicing finding the second derivative and reviewing that implicit differentiation process. So hopefully that helps make a little bit more sense of this. I know there was at least one question that just said directly find the second derivative, and some of the contextual questions had us finding the second derivative. This one involved the quotient rule, which was more typical of what we did with second derivatives. So we saw a lot of them, but it's been a while. If you want to practice, this is question 10, I believe, in your packet. And this one says directly find the second derivative, evaluate it at a point. This does not have the follow-up analysis with it, but this would be great practice for another second derivative.